So, we will talk about control techniques. So, you have linear control and so why do we need this control technique, by the way? If we know that we just have a LC power stage, power switches, you just feed the duty cycle and get the output, PWM. Yeah, so your load is varying. If your V in and V out is fixed, then you can calculate the duty cycle, okay, based on your V out by V in ratio. But the problem is when your load changes, your IR drop in the power stage, because that is not ideal, that is lossy. Your power FET will have some RDS on, your inductor will have some resistance. So, IR drop will change. So, duty cycle has to change, and we already looked at how much delta D will be required, okay, in order to compensate for those losses. So, that is why you need a feedback control, so that when any changes in your basically parameters will get compensated by the feedback loop, so that your output is regulated. So, this will take care of all the changes your due to temperature or due to load current or due to line voltage also. If your V is changing, your duty cycle has to change. So, everything will be taken care, and that is why we always need a feedback control here. Otherwise, we could have achieved the same voltage simply by feeding the fixed duty cycle, that is it. So, this linear control, this is your voltage mode or current mode. This is mostly based on ripple actually. This is also called ripple control. Hysteretic, constant on or off time. Okay, so this is fixed frequency control. This is variable frequency. Okay, think about constant on or off time. You keep one either on or off time constant. Okay, so let us say I keep on time fixed on time, and I keep varying the off time to change the duty cycle. So, your frequency has to change, that is why your frequency is variable, and same thing happens in the hysteretic control also. So, we will talk about in detail later. So, we will start with the voltage mode control, and we will do all the dynamics with the voltage mode, and later we will see what happens in the current mode, but most of the these buck converters are built using voltage mode actually, if you have a wide range of duty cycle. So, that is why our main focus will be voltage mode, but we will briefly talk about current mode also, how does it function and what all compensation it requires. So, let us start with voltage mode control. So, what we will do, this is your VDD. So, now onwards I will be just simply calling it gate driver. Which takes the PWM from your PWM modulator. Okay. this is your ramp. If this is going 0 to Vm, so the amplitude of your ramp is minus plus, this is your VCTRL. It has to come from your amplifier. So let us say I am drawing a simple amplifier, op amp. Vref, L, C, R. So this will give your beta factor. R load. Okay. This is your VSW switch node. So if I want to do loop gain analysis for stability purpose, so the way the reason we call it voltage mode control, because your duty cycle is only controlled by the voltage, you do not have any current component here, and we need a amplifier because I have to regulate my output or feedback voltage to Vref. So you need a very high DC gain. Okay. So which means this amplifier has to be very high gain. High gain amplifier. So it will take the difference of Vref and VFB and will change the control voltage. Okay, so if I assume this gain is very high, 1000 or so. So 1 millivolt change in the input difference will change your control voltage by 1 volt roughly, which means, and let us say this is 0 to 1 volt Vm. So what is the maximum V control you require? 1 volt only to achieve 100% duty cycle, which means the difference between VFB and Vref will be 1 millivolt or less for the output voltage you want to regulate it. Okay, that is why this gain matters. If you make the gain 40 dB or so, 100, then that error will increase, and we already talked about this sources of error in LDO, if you remember. So gain was, DC gain was one of the factors, because you are in the closed loop, it is A over 1 plus A beta. So if A is very high, only then you get 1 over beta, otherwise A will also come into picture and it will cause error in the output. So that is why we need a very high DC gain for any regulator actually, irrespective of whether it's switching or linear. So that in order to meet that requirement, your A should be very high. So if I want to do the loop gain analysis of this, that is where we start with to analyze the stability of any closed loop circuit. So what all I require? You have to break the loop, and then you have to find the transfer function of each stage, just like you did in the, let us say, 2-stage LDO you had. So you first find the transfer function of first stage, then second stage, then it is a cascaded, you cascade it and you find the final transfer function. So same thing you have to do here. So loop gain analysis is required for stability. So, this step 1. Break the loop. So, we usually prefer to break the loop at high impedance input, where input is going at the high impedance. So, you can break the here. You can break here also, as long as you make sure that your capacitor remains on the other side. I mean, if you break here, capacitor will come at the input and you will not get any resonance LC. So, you cannot break this LC actually. You can break here and move this part on the other side. So, that will remain, but VFB is the preferred point. So, break point for loop gain analysis. Second step, find the transfer function of each stage in the loop. Okay, so what all we have in the loop? So, number 1, you have feedback factor. So, what is the transfer function of this? I will call it T1S, let us say, or HM1S. H of FBS. Okay. What is this? 1 over beta? No, sorry, it's beta, huh? Which is R2 by R1 plus R2. Then second, after that what do you have? Amplifier. And this is high gain bandwidth amplifier. So, I can assume that pole due to this amplifier is outside your UGB. So, I will just assume that it has a gain of A, okay, for now. So, H of amp S equal to A. Third, what do you have? After that, what do you have? PWM modulator, huh? So, what is the input and output here?
Output is the duty cycle.
And input?
Is the voltage.
Voltage is V control. So, which means how will you find the gain?
Gain is 1 by VP.
No, what is the output? Output is the duty cycle, huh? Delta D over delta VCTRL. Now, if your ramp has a amplitude of Vm, which means going from 0 to Vm. So, what is your duty cycle? It is going 0 to Vm, huh? So, at 0 we control, what is the duty cycle? 0? At 0.5 Vm, what is the duty cycle? 0.5? So, it is a linear, huh, function. So, what will be the gain? Can I say D equal to VCTRL over Vm? Correct or not? So, if you differentiate this, (1 by Vm). Okay. So, this is your, I will call it GPWM 1 over. After that, what do you have? Gate driver. What is the input and what is the output?
The signal gets
What is the input output of this? So, gate driver, let's say, let's include the switches also here. Huh? So, gate driver plus switches, which means you are feeding VPWM here and you are getting VSW, correct? So, both are PWM here. So, what is the difference between VPWM and VSW? It is only the level shifted signal, that is it. So, this will go at VDD and you do not know the level of VPWM. This could be anything depending upon your comparator. So, and that does not matter as such. So, it will get level shifted here and you will get the output. So, at the PWM you are getting a basically duty cycle input and at the output you are getting. So, VSW is what? D times VDD. So, if I call it D in and no, in fact it will remain same actually. So, your VSW is D times VDD. So, if delta of VSW over delta of D, it will be nothing but VDD, correct. So, change in this output voltage VSW with respect to input, which is duty cycle. Okay, because in the case in the third stage we are considering that my output is duty cycle. So, the input to fourth stage should be duty cycle only. So, input is, that is why I am considering D here. VPWM is nothing but D for the small signal. So, the gain is nothing but, so if I call it G of, let us say, power stage equal to VDD.